So yesterday I was about to talk on the adsorption. Here we are talking about soil factors. Now, when we talk about the soil factors, the most important aspects are clay minerals and organic matter. The clay minerals and organic matter have got negatively charged surfaces, whereas most of the herbicides will present positive charges. So we have ions and molecules from herbicides, which are electrically attracted to soil colloids or colloidal surfaces, which could be clay minerals or organic matter. Now, ions are charged molecules of herbicides. So the herbicide needs to be in an ionized state before it can be attracted to the clay minerals or to the organic matter. And that process we call it adsorption. So the adsorption of herbicide ions and molecules occurs on the clay and organic matter surfaces. So these are the components of soil which matter as far as herbicide adsorption is concerned. What it means is that the clay minerals and organic matter surfaces can hold the herbicide molecules via attraction because of different charges. Herbicide molecules which are now left in the solution become available for plant uptake or microbial action. This is the solution which is likely to kill the weeds. Now, what can happen is that sometimes you may have a very little amount of herbicide being available, and the weeds may survive because the dosage may not be enough. So you'll find that for our pre-emergence herbicides, we use clay content to calibrate the amount of herbicides which, or to calibrate the amount of the herbicide which should be applied per given soil. In Zimbabwe, we use clay content. In other countries like Europe, US, and other temperate countries, Russia, and so on, they use organic matter to adjust their dosages. Because these two, organic matter and the clay minerals, adsorb the herbicide after application. Now, there's a process which we call desorption. This is the movement of the herbicide ions from the clay and organic surface back into the solution. So, adsorption, it's taking in the herbicide by these units, and the release of the herbicide is desorption. Or we can say that the reverse of absorption of adsorption is desorption. So the two processes, adsorption and desorption, are in a state of equilibrium. This is a diagram showing the clay particle which is negatively charged or which is presenting negative charges on the surface. And you have the herbicide ions being positively charged, and these are attracted to the clay particle, and they will surround the clay particle until the final charge is zero, which means that the clay particle is fully covered by the positive charges from the herbicide. Hello, hello, hello. Okay, sorry about that. So clay particles always attract uh, herbicide ions which are charged. And the free herbicide which is in the solution will be available to kill the weeds. So there's always adsorption and desorption processes which are in equilibrium. Now, if you have the herbicide which is negatively charged, it is going to be repelled by the clay mineral and it will be lost. So there will always be desorption. I think Barneville could be an example. We may have to check this. That's why it is easily lost in the soil. Then organic matter. Now, with organic matter, there's the process known as sorption, because the whole herbicide will actually penetrate the organic matter. And sorption is known as partitioning of a non-polar herbicide into organic matter. So the herbicide should not carry some charges. It is just taken in by the organic matter. So here's an example where we have organic matter and we have got the herbicide in solution which has to penetrate the organic matter. Sometimes we calculate what has been absorbed or soaked by the organic matter and what is left in the solution. Now, the two concentrations, the one inside the organic matter and the one outside the organic matter, give us a value known as the KD value. This is the ratio of H1, which is the herbicide which is already in the organic matter, and H2, the herbicide in the solution. Sometimes in temperate countries, they can use KD values to adjust their herbicide rates. Another value which they calculate is KOC, which is KD divided by the mass of the unit of organic matter. So that value can also be used to adjust herbicide rates where organic matter is an issue. Now let us talk about ionization properties of the herbicide. By ionization, we are saying that sometimes the herbicide can dissociate into its components, which could be negatively charged or positively charged. But the main herbicide, if it is positively charged, we describe it as cationic. And the cationic herbicide is likely to be bound very tightly to the soil particles. We have got examples like paraquat and the glyphosate, which lose soil activity as a result of this strong attraction to soil colloids. The molecules will be tightly bound. These herbicides are very sensitive to quality of water which is used during spraying. If it is dirty water, the herbicide will get attracted to the particles inside the water and we may lose herbicide activity. So there's loss of herbicide efficacy due to use of dirty water. Sometimes it may be difficult to get clean water for spraying if you are in the field. So remember that there is loss of herbicide efficacy when the herbicides come into contact with the soil, especially paraquat and glyphosate. This is paraquat with positive charges, so it can be strongly attracted to the soil particles. Here I've got a diagram showing paraquat and glyphosate being strongly bound to soil particles. On our left, we have got a soil colloid, which could be clay or organic matter. For our case, it could be clay. So paraquat, which has got two charges, is strongly attracted to the clay particle. Now, with respect to glyphosate, you should understand that glyphosate has got negative charges on its molecule. So we expect it to be repelled by a similar charge on the soil colloid. But what can happen with glyphosate is that when you have clay particles, they may attract calcium, ferric or ferrous ion. It could be aluminium, which exist in the soils. Now, the presence of either calcium, ferrous ion, or ferric ion, or aluminium will cause some of the charges not to be saturated. So, if you have, for example, calcium surrounding a soil colloid or a clay mineral, because it is positively charged, there's going to be an excess of positive charges surrounding the soil colloid. Then, in that case, glyphosate will now be attracted to calcium, which is attracted to the soil colloid, and they will form a very strong bond, leading to the fact that glyphosate won't be available or it will lose the activity. Now let us look at the effect of soil pH on a pre-emergence herbicide, for example, atrazine. Now on low soil pH, let's say 4.3. Now atrazine will attract hydrogen ions at position 2, at nitrogen, which is at position 2 in its ring. And this process where atrazine will gain hydrogen ions is known as protonation. So there are two nitrogen positions in the ring of, if I may clarify this, there should be two nitrogen positions on the atrazine ring or molecule. And these positions will attract hydrogen ions, and the process is known as protonation, gaining hydrogen ions. The result is that the molecule of atrazine is going to be positively charged. So the atrazine charged molecule will now be attracted to the negatively charged soil particles, which could be clay minerals. So there's that strong attraction under low soil pH because the atrazine will have become protonated or charged positively. This will cause atrazine to lose its herbicidal activity, and this problem is common in Zimbabwe. The rate of breakdown under this situation of low soil pH is also rapid. So there is fast breakdown of atrazine. So we can easily lose it. Here we've got two situations where we have low soil pH. We have got hydrogen being attracted to the nitrogen bonds, therefore forming this positively charged molecule. In an area where we have higher pH, that protonation will not take place, and hence atrazine becomes available to kill the weeds. Now, the effect of soil pH on atrazine efficacy at a high pH of above 5, atrazine is less protonated and it is active to kill weeds. So atrazine will be available in the soil. It is not adsorbed to the soil particles, so it means it is present in the solution in a sufficient quantity to kill the weeds. So increasing soil pH will actually improve atrazine efficacy. We can increase soil pH by liming when you are correcting the soil pH, although this will also make nutrients available to the crops. It will also improve atrazine activity on weeds. So this is a diagram showing atrazine with two positive charges being strongly attracted to a soil particle with a soil pH of 4.3. So at low soil pH, atrazine is tightly bound to the soil particles to the extent that we may lose its efficacy. In contrast, at pH which is greater than 5, there is no attraction of atrazine to the soil particle. So you will see that most of the atrazine is in the free state, in the free solution, and it is ready to kill the weeds. This is the ideal situation when we should apply atrazine so that we can kill the weeds. Now, in Zimbabwe, we use the calcium chloride scale for measuring pH, and we have three categories. Normally, we have a pH which could be 4.5. It means the soil is very acid. If it is between 4.5 to 5, we say the soil is strongly acid. Above 5, we say it is satisfactory for production of most crops. This is the ideal soil pH. Well, these are some of the soils which were taken across some communal areas. You can see the variation in soil pH. Guruwe 4.8, Makoni 5.8. The lowest pH was from Chiota communal area with 4.5. So using atrazine there could be, problematic in some of those soils. Otherwise, the atrazine may fail to kill the weeds. But in some areas like Wedzane Cairo, where you have a pH of 7.6, this is quite ideal for herbicide, for atrazine activity. Bikita 7.6, again, very good soil pH. Chivu 4.5, Narira, this is low soil pH, more or less similar to what we have in Chiota. But of course, the soil pH can be managed by putting in lime. I understand there has been a very big program to lime some of these soils. And the Pfumvudza package now contains sometimes lime so that farmers can put lime when they are growing the crop under the Pfumvudza scheme. So, how to reduce soil pH problems? Uh, Addition of lime to the soils can improve soil pH. Even manure addition can actually raise the soil pH. Now, there are some molecules which are not charged, but which are attracted to soil particles. So they exist some weak attractive forces among nonpolar molecules. Nonpolar molecules are those which are not charged. The molecule has got a zero charge. So in this case, soil pH may not affect such herbicides like trifluralin, which has a zero charge. It's not affected by variations in soil pH. So this is trifluralin with a zero charge on the molecule, and it is not influenced by soil pH, and it is attracted to the soil surfaces by what are known as the van der Waals forces or just weak forces. So you should be aware that there are some herbicides which are independent of soil pH. Now, still talking about the soil, let us check the role of soil moisture. Now, if the water is added to the soil, it can compete with herbicides for the binding sites on the soil surfaces or soil particles. This is very important for EPTC. EPTC has to be applied under dry conditions so that it can be attracted to the soil particles. Herbicides tend to bind tightly to dry soil. That's why we apply EPTC under dry conditions. If we do it under wet conditions, we may lose the herbicide. You must be aware that under stress, the pre-emergence herbicides may not work because they are not available to the crop. This is the first diagram is showing soil water or wet conditions. Under wet conditions, you will have water surrounding the soil particle or colloid, and it displaces the herbicide so that it is in the solution. Under dry conditions, you will have more of your herbicide uh, surrounding the dry soil, and it is not available to kill the weeds. Under wet condition, the herbicide is available to kill weeds. This is how soil moisture can influence herbicide efficacy. It can be a bit tricky to understand, but if you know that under wet conditions you have more water molecules being attracted by the clay surfaces, therefore releasing the herbicide into the solution. But the opposite happens under dry conditions where you have more of the herbicide surrounding the uh, dry soil. So addition of soil moisture may activate the herbicide. When we say activate the herbicide, we mean that the herbicide will be reached or it will move to the weed zone. This is what we want so that it can kill the weeds. So adequate moisture ensures good weed control. Dry conditions will lead to poor weed control. Now we move on to photo decomposition. This is the effect of light on herbicide molecules. Now, the herbicide molecules which are affected by light or photo decomposition, they should carry carbon and nitrogen. For example, atrazine is likely to undergo photo decomposition. And the wavelength should be between 290 and 450 nanometers. This can cause excitation of electrons, which will lead to breakdown of these molecules. They can cause bond rupture, oxidation, reduction, hydrolysis, substitution, and isomerization are some of the chemical processes which are caused by which are caused by light. And this is what can lead to photo decomposition of the herbicides. In fact, if we apply atrazine under dry conditions, after 3 weeks, we may lose this herbicide through photo decomposition. Even if the rains come, there is nothing to reach to the weed zone, and we will have poor weed control. No wonder why we should avoid applying atrazine or any pre-emergence herbicide for that matter under dry conditions. If we put it under dry conditions, irrigation should come immediately. Number 7, the last process, chemical decomposition. This is a straightforward chemical reaction. It's like a test tube reaction. No living organisms are involved. But soil pH can play a role in determining the dissociation of the herbicide molecules. And these hydrolysis, oxidation, and reduction are some of the chemical reactions which can take place if you apply the herbicide on the soil surface. Herbicides such as triazines, sulfonyl urea herbicides can undergo hydrolysis, especially under acidic conditions, we can easily lose these herbicides. So that was the last the last process. Now, here I'm just giving you examples of some studies which were done in Zimbabwe on herbicide persistence. Chivinge and Mpofu in 1990, they did a study on metolachlor, terbutylazine, atrazine, and prometron, and they found that the persistence was up to 12 months under sandy soils. But when they grew groundnuts, although groundnut could peak uh, phytotoxicity in the first few weeks, the groundnuts grew out of that phytotoxicity and the yields were not affected. Probably it was a matter of the genotype, or there could be some genotypes which can be affected. Zaranyika and Nyandoro in 1993 demonstrated the persistence of glyphosate under aquatic conditions. And they said that during the first few weeks, there's a rapid disappearance of glyphosate. And then it is slowly disappears with time. Now, Mushambi in 1993 calculated what is known as the half-life of a herbicide. This is the time taken by the herbicide to degrade to half its dose, to half its original dosage. It's a measurement which is used to study pesticides in the environment. So the half-life of atrazine was 59 days for ready soils and 24 days for sandy soils. You can see that atrazine could disappear very fast in sandy soils. If you start with the 4 liters, the time taken to reduce it to half is what is called the half-life. And it is used as an indicator or as a measurement of soil persistence. Now, this is the one of the studies which was done under conservation agriculture by one of our students in a maize soybean rotation. In maize, atrazine was being used. So he used the soybean to test whether it could be affected by atrazine. So these are the growth. This is the growth of soybean. You can see if the lines are separating, probably there's a bit of effect of atrazine. But in most cases, the atrazine residues did not appear to suppress soybean. He did this at 2 sites, I think Henderson and the university site. Henderson red sandy soils, and no, it was Dombosha sandy soils, and use it farm red soils. Now let us look at some factors which are likely to influence herbicide persistence. We have got dosage. If you put high dosages, this can increase herbicide persistence. No wonder why we need to calibrate our sprayers so that we do not over apply these herbicides. Otherwise, we will have a lot of soil persistence, herbicide persistence. We may need to reduce herbicide doses, use herbicide mixtures, or bending. Number two, binding affinity, the attraction of the herbicide to the clay minerals. So herbicides that are strongly attracted to colloids are less available for microbial degradation, which means the herbicide is likely to last for a long time. So clay minerals, long herbicide persistence is expected, and in sandy soils, we expect short herbicide persistence. Soil temperature and moisture are important in herbicide degradation, and hence this can affect herbicide persistence. For example, atrazine could last for 9 months under in a dry season, 7 months in a wet season. So the dryness of the soil can cause uh, a long persistence of the herbicides. High temperatures increase degradation. I think some of our temperatures, like this month and November, even up to December, can cause a lot of pesticide degradation in the environment or herbicide degradation. Now, there can be soil amendments if we wanted to uh, adjust or if we wanted to uh, make some crops grow in affected areas. We may add organic matter, e.g., cattle manure. This can decrease the herbicides in the soil by adsorption. It can also increase microorganism population, which can enhance herbicide degradation. Remember, these microorganisms, once they sense the herbicide, they are going to prepare the appropriate enzymes which will degrade these pesticides. So I will summarize uh, probably in one slide the processes that affect herbicides when they enter the soil environment. There are 7 of them, which we have actually talked about. So if you want to remember the processes, you just use this slide and try to figure out how the herbicides are affected, especially when they are applied to the soil. And I indicated that under microbial activity and the role of plants, it can be a long story where you talk about phase one and phase two, phase three of herbicide degradation, which is supported by a lot of these enzymes. So this is it. So I will stop here.